of K for FHF. Yesterday we proved this I-Pylons K. You can do the same for FHF. So let's say for K equal to 1, okay. This is in this appendix, also some extra information. Like, if you are curious, you can find it. Okay, I will always start every lecture with a summary of what I did in the previous lecture, just to remind you what are the main points of what we have seen. Okay. And yesterday, what we have seen is first, what is the definition of an instanton? Instanton. It's a solution. This is a general definition which is valid in any quantum field theory or even quantum mechanics. A solution of the Euclidean equation. Okay. The importance of this fact is that they are the leading contribution to they provide the leading contribution to path integrals. And essentially what we have seen is that if you have a correlator in any quantum field theory, this you can write as the integral of I into the I into the minus. Okay, and this in general you can write as a sum over all possible instanton sectors of some numbers e to the a squared. Okay, now this is a gauge theory. In general, if this is not a gauge theory, what you will find here is the action in the instanton. And typically, instantons are classified by a topological number. Therefore, typically this is a sum of integers of some coefficients and the action evaluated at the instanton level. Okay. Now for gauge theories, we have seen that for gauge theory, essentially gauge theory is given by a field strength or a connection, and the equation, you have two equations. One is the Bianchi identity. And one is the field equation. And a simple solution, we simply say that Fermion is equal to plus minus Ft. By the way, you could say why plus minus, why not 4 or 5 or anything else? Okay, what you can see is that the star of the tilde of the tilde, the dual of a dual is the field itself. It's very simple, just using the definition of dual. This means that dual can have eigenvalues only plus or minus. Dual square, in other words, you can write also this that's saying that the star square is equal to 1. Star means the dual. Therefore, this operator have only eigenvalue plus or minus. This means in a Euclidean space, F can be either self-dual or anti-self-dual. And this is important because if you would be in Minkowski space, the star square in Minkowski would be minus 1. This means that here you should have plus minus I. Therefore, you see, this solution, self-duality, can exist only on a Euclidean space. You cannot have a self-dual field in Minkowski space. Then the next step was the observation that the instantons are classified by this number, K, which is topological number. This is a topological number, which essentially measures how many the maps between the S2, an S2 subgroup of the gauge group you have, to the sphere. I remind you that S2 have the topology of a sphere. So this really, this number K measures how many times the SU2 wrap the sphere at it. Okay? So this is a topological number. You can classify any field configuration, you can classify with this number, and you can see that the instantons are the minimum of SE for a fixed. The minimum means that they will give the leading contribution, remember, to the path integral for that particular topological set. Okay, then we see the simplest solution, it was K equal to 1. Okay, and the solution was written in this way. Sorry, this U, yes. Well, okay, there was a question yesterday. Why? Okay, this U is a gauge. Okay, this is log. This is a constant matrix. This is a gauge transformation. Okay, this is a solution. Now you act with a gauge transformation, and you find another solution. Now the question yesterday was, sorry, why is a gauge transformation? We should be the same solution. No, because the instanton break the gauge symmetry. Essentially, you see, this configuration is not invariant on the gauge. This means that the instanton break. By the way, notice that any parameter in the instanton solution is related to a symmetry break, broken by the instant. Okay? What means by that? For example, it's 0. What is it 0? It's the position of the instant. The presence of the instant breaks the Poincare invariance. R4 has the Poincare invariance, means that any point in R4 is the same. But once the instanton is there, it's no longer true, because the instanton breaks this. Then it's 0 sign the breaking of Poincare symmetry. Poincare. U signs the breaking of gauge symmetry. And rho signs the breaking of conformance. Rho is a scale, is the size of things. You see that any gauge theory, the gauge action is always, in 4 dimensions, is always invariant. Let me write it this way. This is, I'm now writing, this is not important for us, but imagine that you're in a curved space, okay? You have a metric, and this is the action of this José curve. And you see that this is invariant on the scaling of, because this is scale like lambda squared, this is like lambda minus 2, therefore this is invariant on the conformance. Therefore, the Jamil action is always invariant on the conformance symmetry. And the instanton break this conformance if you have a size. Once you have a size, the things are not invariant. Therefore, this is important you remember. It's good that you asked me this question, because I also were confused. And this is true in general. Every time you have a solution of an equation, all the parameters are always to every symmetry that you break, there is a particularity. Okay. Go ahead. Okay, then the next step was to construct explicitly the solution. And the main observation was trying to look for solutions that were. Okay, this was the simplest case that lead to a solution like that. But there was a general construction of this, which is called ADHM construction. Okay? And this construction is based on two matrices, two rectangular matrices. One is delta, which is n plus 2k times 2k. And one is u, which is n plus 2k times n. Okay? This construction is based on this matrix, and it's based on this assumption that this matrix is given by a matrix, constant matrix, plus its n, the depending on its, is very simple. It was just this p. B was here, C minus. Equals n. Okay? But again, let's write this matrix also. Okay? This was the idea. You take these two matrices that satisfies these conditions. Let's try to this form. Now it's incomplete. Okay, the ADHM construction say that if you can write a self-dual connection by taking a matrix U, which is n plus 2k times n, and writing this expression, and a matrix, and this U is the kernel of a very simple matrix. Okay? Then essentially what you do is you take any number here that satisfies this condition. This is called ADHM constraint. Okay, and now we will write explicitly. Yesterday we didn't write in good points, but let's write this question better. Let's first take a theory. You take any matrix here, any numbers here that satisfies this condition. Compute what is U. What is a matrix U that satisfies this condition? And plug here, then you find the question. Okay? Good. Let's see what is this. Okay? Let's remind this was the matrix K by K, and there was the identity 1 by 1, 2 by 2. Therefore, let me call this A and this B. Therefore, let's compute this. Delta bar delta is A bar A plus its n A bar Bn plus B bar A plus its n B bar n B n. Again, always remember, index up and down make no difference. Okay? Now, what is B bar n Okay, let me give you some identities of the Dirac matrices. We'll write here some identities that can be useful. Find something useful, I write here. For example, one identity is this sigma bar alpha dot alpha times sigma n alpha beta dot sigma bar dot alpha sigma n alpha beta dot is equal. If I take the symmetric part of this is delta n delta alpha dot. This is just an identity of the Dirac matrix. Then you see this is what I have here. No? Because this is Vn, we say that it's proportional to sigma n. I'm taking here the symmetric part, because this is xn. Therefore, this is automatically proportional to delta. For this is proportional to delta alpha dot. Okay? Therefore, this is already in this form. The constraint says that delta bar delta should be proportional to delta. F is an arbitrary function, whatever it is. Okay? Therefore, this, don't say anything. This is okay. This part, again, is the same. Because if I write A is 2 by 2, 2k times 2k. If I write this A alpha dot, which is a matrix k by k, like An sigma n alpha dot, okay? You see that this is again sigma bar times sigma plus the other way around. Symmetric. For this is again proportional to delta alpha dot. Okay? Then the constraint of ADHM can be written in this way. No? A bar times A, which is just, you see now it's a constraint just on the numbers that you put on the moduli space. Okay? This is just an algebraic constraint. Let's write it explicitly. This would say that omega bar alpha dot times, okay, it should do A bar is omega bar A bar times omega A, and this is just omega bar alpha dot omega beta dot. Let me write even also the indices of omega, so you have this alpha dot I u omega beta dot. Let me get I u j beta dot. Okay. I will write here down. This is omega bar alpha dot I u omega u j beta dot plus A bar alpha dot alpha I k times A alpha beta dot k j. All these should be proportional to delta alpha. Okay. This is what is called ADHM. And we can count the number of parameters that we have. We have initially 4 kn parameters coming from W, k squared parameters, 4k squared parameters coming from A, and you have how many relations? You see, I and j goes from 1 to k. Okay? And there are 3 relations, because you see, this is proportional to delta. Another way of writing this is this is a matrix 2 by 2. A matrix 2 by 2 have 4 numbers. We are saying that the diagonal, this should be proportional to the diagonal. We don't put any constraint here, this F. Then we have 3 non-trivial relations. For example, we can multiply this by tau c. We can project this by tau c. You understand what I'm saying? The part that is proportional to the identity, I don't care. This is not, can be anything. All the other 3 numbers, the part proportional to sigma 1, sigma 2. I mean, a basis is sigma 1, sigma 2, sigma 3, and the identity. The identity part, there is no constraint. There's constraints only on the 3 parts proportional to tau 1, tau 2, and tau 3. Therefore, these are 3 k-square constraints. And then there is also the U1, the UK C, or C. All these matrices, you can act with UK. The way it's therefore, there is an extra k-square symmetry. This is just rotation of this matrix with UK. And this gives 14 numbers. Okay, it's clear. This part I forgot to add this. Okay, therefore, the main point is you start from 4k squared plus k squared, from 4kn plus 4k squared variables. Satisfying this constraint is already reduced to 4kn variables. Compute the u, plug in this formula, and you get ADHM. A self-dual connection. It's clear? You see, everything are numbers. All these are numbers. All the dependence on x is triggered. You see how hard this is very complicated, depending on x for k equal to 1. If you do this for k equal to 2 and c, the dependence on x is very complicated of the self-dual. But it's very simple for the data. The nice thing of this construction is that you start from something very simple. You plug in these formulas, and you get the most general self-dual connection. Okay. Okay, that's all. This is, we finish here yesterday. Okay. Now, let's do the simplest k equal to 1. Now, using this is just to show you how you can, in general, proceed. Let's say we want to now reproduce the solution we said yesterday, k equal to 1 is 2. For k equal to 1, n equal to 2. We want to reproduce this construction. Okay? For n is equal to 2, k equal to 1. Okay? Therefore, omega is a matrix 2 by 2. And let's take, you see, omega is a matrix 2 by 2 and satisfy this constraint. Okay? Now, the simplest thing you can do, and in this case the only one, you see, are 4 numbers and satisfies 3 constraints. Therefore, there will be only one solution for omega. And there is a trivial solution. Just take omega proportional to the identity. You take omega proportional to the identity, omega bar times omega is the identity. Okay? Therefore, this is the solution of the ADHM equation. You see, delta bar times delta, if you compute here, this would be rho squared plus x squared. Again, here, you use this relation. No? You have x bar, okay, let's compute delta bar. This will be rho x bar, xn sigma bar alpha dot alpha rho, and here you have xm sigma alpha beta. Okay? Then this is equal to rho squared times the density times delta alpha dot theta plus xn sigma bar, sorry, this is n, sigma bar n times sigma n theta. Okay, but this is symmetric on the exchange of effects n. Therefore, I can put here only a symmetric part. And this symmetric part is just the delta. Okay, therefore, this is just rho squared plus the delta of mn, therefore this will be plus x squared delta. Okay, therefore this delta satisfies the ADHM constraint. Okay, I have already delta satisfied the ADHM constraint. Then, sorry, I always go in the opposite direction. I don't want to cancel something. Then I should compute now the u. No? And the u is I want this relation. So u bar delta should be 0. Okay? Therefore, I can take, for example, for u bar, I can take something proportional to minus x to 1. This is obviously u bar times delta is 0, no? Give minus x bar, okay? U bar times delta give minus x2 to 1 rho x2, sorry, I take a rho here. Okay. Then this is equal to minus rho x22 plus rho x22, which is okay, this is a trivial solution. Okay, therefore now I have already u bar, therefore I have also u. U is just a complex of that. Sorry, what did I say here? I wrote the opposite way. Rho 1 minus x2. No?
I think it was.
No, it was correct. Sorry. Yeah, it was correct. Sorry. Then was I want that this is 0. Therefore, I should write here minus x22, and I should write here rho. Okay. Okay. Now u. What is u? U is the bar of that. Actually, this will be like that. This will be minus x. Ah, sorry. This should satisfy also the condition u bar u is equal to 1. Okay. Therefore, I should normalize this. The bar of this is again rho squared plus x squared. Therefore, I should write here 1 over the square root of rho squared plus x squared. Okay, now then u is the bar of that. This will be minus rho bar x bar rho. Rho is real. Therefore, let's compute a. An is u bar dm of u. This is u bar times u. Here there will be a factor 1 over rho squared plus x squared. Okay, and now I should compute this u bar, which is minus x rho, times dm of u, dm of that. Then this is dm of x bar will be simply minus sigma bar m. Remember, x, every time I write x, I means okay. Therefore, the derivative of x respect to m is simply sigma.
Francisco, does it still work with the normalization like that?
Because there was this condition. U bar u should be equal to 1.
Yeah.
Therefore, you see that if I take u bar times this times, if I take minus x rho times the bar of this, which is x bar rho, okay, this is again x squared plus. You always using this factor, sigma bar, every time I symmetrize, because this is xn, x6 bar is xn sigma n times sigma bar n. And every time I symmetrize this is proportional to delta, and it's proportional to delta n, this will give the x. Okay, I were here, no? I were here. dm of u, dm of rho is 0. Okay? Therefore, we get only this term. This is x sigma. Let's write down the components. X n sigma m alpha beta dot sigma bar beta dot is okay, sigma n. So this was xn sigma n, and this is sigma bar. Sorry? Everything divided by this was x, and then everything divided by rho squared plus x.
Sorry? When you have to take the derivative of the square root in u also have the square root.
Good. Good. It's a, I just take the derivative here. I will wonder if I get the wrong answer. Because remember, we should get here the sigma mn. Okay, let's, okay, I forgot. I take already the derivative here. The dm of that is sigma n. Okay, plus taking the derivative here. Okay, plus 1/2. Derivative of rho squared is give 1 over rho squared plus x squared in the denominator, an extra 1. The derivative of x is 2x, 2xn, and then you get again u bar. Sorry, u. This was u. I'm taking the derivative. I'm taking the derivative of this guy. Okay? This is also. Okay, so I should cancel something here. Otherwise, I will get it. Then we say AM is U bar dmu is equal to u bar, there is factor, overall factor. Let's take the two terms separate. Rho squared plus x squared. There is a first factor coming from this term when I take the derivative only here, and this was given this term, sigma n, sigma bar n, alpha beta. This was the first part when I hit with the derivative. Okay? Now let's try to explicit these terms. This was u bar is plus u bar times when I add here the derivative in this x. The derivative in this x is 1 over rho is 1/2, 1 over rho squared plus x squared, and then there is the derivative in x is 2x, and then all the rest is simply. Okay? Now I have this. I add here, I will get really 1 over rho squared plus x squared to the 3/2 xn
minus, right?
You will say 1/2, but then you have a 2 coming from
No,
the
minus that. Because
minus that. Okay? Therefore, you see that all this, I can write this as 1/2 over rho squared plus x squared. Therefore, all this is again u. Therefore, what you have from extra is xn minus and a rho square over x. This cancels with that. And this is yes. Why I do like that? Because I know that u bar times u is equal to 1. I don't need to do this. Okay? Therefore, what I get is.
I think
so here there was also an x. Okay? Therefore, I get x. Okay, now let's do the following. This part is this product of the matrix. I can write as the symmetric part plus the antisymmetric part. Any matrix I can write as the sum of the symmetric part and the antisymmetric. The symmetric part is proportional to the derivative. Therefore, you get this symmetric part is delta n, and then this delta n is here is n, and this is exactly this term. So you see the symmetric part cancels with this term. Okay? While the antisymmetric part give my final answer. This antisymmetric part is twice sigma n. So this is twice. There is a plus sign. Sigma n. Okay, which is exactly the truth solution we yesterday proposed, let's say, because at that time we didn't prove. Okay, then you see what is the idea. You start with any number. Write this ADHM constraint that now I cancel. Write the ADHM constraint and solve. This is an algebraic equation, that numbers. X times x squared minus y cubed, you solve in any variable. And then you compute already delta. Now you take delta times u bar, this is again an algebraic equation. You solve again. Just say, okay, you find the x cubed y there, you find what is u. You plug in this formula, and you get A, and from A you get. Okay? the nice thing is that for most of the computations that we will do, we will see in this course, we will never need to do that. Already from the fact that this is of this form, we will see how you can get all the interesting information in the quantum field theory without never compute a set-dual collection. I have never seen a k equal to 3 instanton, the f of k equal to 3, I have never seen in my life. And I work instanton already for 10 years. Okay? Then this is just important that you have this structure, but you will never need to write explicitly what is f. It's nice that you have k equal to 1 because you can already imagine that all of them will be of more or less of this type. They have a position. We already see that once you understand SU2 instant, you understand everything. Because SUN is just SU2 inside the SUN, and then you have always positions and just embedding of this SU2 inside the SUN. So it's very important you have k equal to 1. And k equal to 2, you can imagine that 2 instanton, 2 position, okay? And they will be roughly of this type, of the type we say, but now you have 2 centers. Okay? When they are far away, they will look almost like the sum of 2k equal to 1 very far. Almost. Then we will start again. But what I'm just trying to say is that you don't need to worry about how complicated this algebraic relation, because you will never solve in your life. People have tried for a long time, for 20 years people have tried. And they were able to do just k equal to 2. And they were able to compute the k equal to 2 integral and so on. Because you understand that once you have the set dual and you want to do a computation, you just integrate over all these numbers. Therefore, you can imagine you have an integral which is 4k times n dimensional. This can get very complicated. And it's exponential of the action evaluating this instanton graph. I mean, this is a mess. We will do for k equal to 1, and we will see how you can get the answer for it. Okay.
Sorry.
Yes.
So to get the final instanton contribution, you have to integrate over all the parameters.
Yes, exactly. We will see it explicitly, because we will do in supersymmetric series. We will do explicitly this computation. But the idea is that you have, once you have f, you should compute s of p of that f. Then you do the exponential and do the integral over all these parameters, all this moduli space of k instanton. This is the quantity that we will be interested in. Okay. Any question? This is the end of bosonic part. Now I will include Fermions. Okay? Okay, we know that all the interesting theory natural contain Fermions. Therefore, we should now think about theories not just with the gauge field, but also with Fermions. Maybe it's a good idea to keep here all these formulas. This formula is very useful. We will use a lot of time because the identity. In other words, U bar U is the identity, but U bar is not identity. This is important. But it's almost identity apart from this. Okay, yeah. Delta bar delta. Maybe we can remind that delta is a matrix n plus 2k times 2k and u is n plus 2k times n. And maybe the indices we can write lambda I alpha dot. And for u, we can write u lambda u. And the index R lambda is n plus 2k. Okay? And here u is going from 1 to n, I is going from 1 to k, and alpha dot is equal to 1. You see, these are all the symmetries of the instant. U is a fundamental of UN, the case. I is a fundamental of UK, is the symmetry of the instanton moduli space. Alpha and alpha dot are the Lorentz indices in 4 dimensions. We say that xn, sigma n, alpha dot is the Dirac matrix. Okay? Therefore, these are the symmetries of the moduli space will be always UK times UN times SO4. SO4 is the same as SO2 times SO2. Sorry, are you familiar with group theory, no? You have already, okay, you understand this. SO4 is SO2 times SO2. And this index alpha dot are always spinor indices of, are the fundamental of these two SO2. Let's say the first SO2 let's call alpha, the second SO2 let's call alpha. Okay? It's just a way to work. Since I will work with fermions, it's better to use the spinor indices than to do the vector indices. These are vector indices of SO4. Okay? In other words, what we are saying is that we can write either xn, this is a vector, or this is equivalent to write x alpha dot, because we know that this. You see, there is no new information. These two objects carry the same information. This is just saying that SO4 is equal to SO2 times SO2. Okay. Then we have the summary. Let's introduce fermions.
Excuse me, just a question. In 4 dimensions, it doesn't make sense to talk about U1 instantons, right?
This is a good question. Very good question. You see, we never talk about U1 instantons because we cannot. No? We see, yesterday we need a SO3 to embed to the S3 at infinity. Therefore, U1 instant do not exist. Still, all this construction you can do also for any one. You don't see any point here where this construction. What happened is that you can imagine take a 4-dimensional space which is non-commutative, a little bit non-commutative. This means that, for example, these variables are not, the commutator is not 0, it's some matrix, CMM. This is something very, very, very drastic. You are changing your space time. In this space, U1 instanton exists. This is a more complicated space. It's no more log R4. Okay? The funny thing is that you say, okay, then I send this sign to 0. Sorry, no. Before doing this sign, you can see that you can compute any computation. Most of the computation, all the computation we will do in this course, do not depend on these parameters. You compute and you see that sign is decoupled. You don't find anything. This implies that if I take psi to 0, you would expect that you find your commutator. But nothing depends on psi. Therefore, you can define U1 instantons as instanton in non-commutative space in the limit where this non-commutative parameter is to 0. Okay? This is just for curiosity. What I'm just trying to say is that in all what I am doing, you can apply for U1. And now you will see people talking about U1 instanton. These are not really instanton. You can imagine this as limits of instantons in a more complicated space. But if you say that there is no U1 instanton, this is correct. U1 instantons do not exist. But it's better if you don't start to discuss too much on that, because people what mean by U instant is a difference.
But this is a statement in 4 dimensions, right?
In 4 dimensions. Sorry, this is a good point. All what I'm saying here is in 4 dimensions. Instantons exist only in 4 dimensions, because you see, say again. The fact that a self-dual instanton exists in any dimension, but the fact that the self-dual connection is an instanton, this is just a 4-dimensional statement. Because in only a 2-4 it can be self-dual only in 4. In 6 dimensions, the dual of a 2 form is a 4. An instanton in 6 dimensions cannot be self-dual. Then there are now new words in which they compute instanton in 8 dimensions, but they define in a different way. For example, they say, okay, I can define an instanton by saying that this object, which is a 4 form, is self-dual. These are these type. But again, all what I will do in this course is 4 dimensions, therefore I will not address any of this.
Sorry, quick question. Originally, we defined instantons as classical solutions to Euclidean.
Yes.
But now you're saying maybe that we should call instantons that satisfy the sum parameter.
No, we already see that this is a solution of the Euclidean equation, plus minus. This is a solution of the Euclidean equation. So you think I don't understand the question?
Well, in this theory, let's say, suppose another theory.
Yes.
Maybe it doesn't. Maybe it has some other. Like this is for the case we're working on.
This is just from the gauge series.
Yes.
Yeah, instanton in general. I mean, you can define instanton even in quantum mechanics, where there is no gauge field. What we are saying that in gauge series, instanton are in gauge series in 4 dimensions, instanton are self-dual connection. But in a quantum field theory, instanton is a completely different. I say you, if you have a quantum, for example, you have a particle in this potential, an instanton is a solution that comes from here to here. It's a completely different solution that I calculate between these two. I mean, it's completely different. We are just saying on gauge series, instantons are self-dual connections in 4 dimensions. Okay, now let's include Fermions. Okay, what is the Lagrangian of a gauge theory with Fermions? Remember, I always say 1/2 and put a trace. You can write 1/4 and put here the sum of the pieces. Trace of sigma times sigma gives 1/2, the extra one. And then you can also have scalars. Or let me call this. Okay, and in general, you can imagine that you can have a theory that has a gauge theory, a gauge field. Some fermions, I label by S, okay? There will be some representation of the gauge group for you to do trace on the representation. This is just a kinetic term. And then you have some scalars, a group of scalars, phi A, they are giving again in some representation. So you have the interactions. Here you have some interactions. Okay? Then now I would like to solve the equation of motion for this field in the instanton. Okay? Now we already looked to this F. Now imagine that you have already found a solution for F. But now, okay, what are the equation of motion of this diagram? Okay, let's see. Equation of motion, okay, the one for the F we have already seen. Sorry, let me call. Let me keep only a quadratic order. This interaction can be very complicated. For the moment, let me keep all the fields to quadratic order, except the instant. Okay? For example, here there will be interaction, Yukawa interaction, psi, phi. This is a term which is cubic in the fields. Therefore, for the moment, I discard all this. I just align my action to quadratic order. Why quadratic order? Because the equation of motion is the derivative of the action with respect to the field. Therefore, if I have the quadratic stuff, the derivative is linear, this actual key, but the Q is already quadratic. Therefore, if I put this field to 0, we continue to be 0. This is an approximation for them. Then, to this order, my equation of motion are okay, let me just give you an idea why I can be so naive in top at this order. We will see that most of the computations that we will do are topological in some sense, are very unsensible to small corrections. Then we will later see more explicitly that it's more like the harmonic oscillator in quantum mechanics. So you compute the energies of the harmonic oscillation using some approximation, some classical approximation, and you find the exact answer. Okay? Here it happens more or less the same. There is a lot of symmetries in the theories I will consider, which is not the standard, it's not any theory of Fermi, but we will consider supersymmetric theories later on. These theories are very restricted by the symmetries, and we will see that this semi-classical approximation, this approximation which I just keep the first non-trivial terms, will give the exact answer. Therefore, we will make an approximation. We will later justify that this gives the exact answer. All the rest, all these terms will contribute, but then there will be contribution from Boson and Fermions that cancel out. Supersymmetry is a miracle. And this is why we are trying to do this computation. Because supersymmetry is such that Boson and Fermions always contribute in a different way. Therefore, there are some quantities, not all of them, but there are some quantities that you can compute exactly with a very simple computation. And since I am not too strong in doing computations, so I will just focus on these quantities. And almost all has been done in the last 20 years are focused on very simple quantities that you can compute, because they are protected by some symmetry. Okay? Therefore, for the moment I am doing just an approximation. I will compute, I will solve. In any case, you should first start from this, and then if you want, you can start to perturb, and say, I find a solution, and then you say, okay, now I exclude the first term, the cubic term, and then you find a correction to the solution. Then you include the quartic term, the correction to that, and so on. Therefore, this is useful anywhere. But the fact that I can stop here is just because I will consider series of the very special. Okay, then what I want is to solve now in general these equations. Okay, the first one we already solved. You already say that A can be solved at U bar EM. Okay. Now I will give all the others, the Fermions. Psi. Now, for the fermion, I should distinguish two cases. I will have fermions that are forming the joint representation of the group, and fermions that are formed in the fundamental representation of the group. Okay? Now, how they will look like? Remember, this is the fundamental representation of the group. Okay? Therefore, if I have a fermion that transforms the fundamental representation of the group, it should be U times something. Okay? If I have a fermion that transforms in the, and this is the fundamental. If I have a fermion that transforms in the anti-fundamental, it should be U bar times something. Okay, this is alpha anti-fundamental. Then, if I have a fermion that transforms in the adjoint, we call lambda, this should be U bar U something. Okay, I should construct the solution with the same ingredient of I use for the construct the connection, because I'm constructing the solution to this equation. You see, in this equation, the only thing that enters is the connection. You see, this covariant derivative is derivative of n plus a. Therefore, the solution of psi will just depend on the connection, and the connection depends just on u. Okay, u delta of this quantity here. For the only quantity that have an index n is u. Therefore, u should appear there in this way. Okay? And now we make an answer for that. We need something with index alpha. Let me. For example, K. I need something with index alpha. Let me introduce. Okay, let me say what is that. Okay, the alpha. I can define the alpha this way. Okay, B alpha is a constant matrix, is a constant that is just the derivative. You see, you remember delta, the dependence of delta means was just linear. and the derivative of delta was a constant. Delta, remember, delta was here, lambda. Delta was a matrix A plus, here there was 0, minus alpha theta. This was delta. Then the derivative of delta is sigma n. Okay? Ah, sorry, I didn't say what is the alpha dot alpha. The alpha dot alpha is derivative with respect to its alpha. The alpha dot alpha is derivative with respect to its bar. Alpha dot alpha, and this is sigma bar n alpha dA. Derivative, d alpha dot alpha is just the derivative with respect to x bar.
Sorry, what are the indices on that anti-fundamental spinner?
On the matrix?
On the anti-fundamental spinner.
All these indices. Okay, let's write. This is a good point. Let's write all the indices here.
Yeah, I'm just saying F as some indices, okay?
This is, remember, U is lambda U. Now,
but B should have an alpha dot.
B is have index lambda, E, let's say J. F is index ij, and this is index A. Okay? Therefore, this is psi alpha U.
And I think the question is if there is an equivalent equation for the alpha dot case. So the psi bar.
So sorry, good. Psi bar alpha dot, I didn't say you still what is psi bar alpha dot, is C. And psi bar T alpha dot, and lambda bar alpha dot is equal to C. Yes, I should give you what is psi and what is psi bar. The instanton, in some way, in the background of the instanton, only half of the fermion can be different from zero. All the other, the second half should be zero. So this is the solution. Sorry. But okay, this is useful anyway. Even if you were not asking that, we can see this is U, lambda, lambda, I, J, J.
I'm very confused. Maybe it's a stupid question, but what is the difference between psi
Don't never say
theta and...
it's a stupid question, because if I don't know the answer,
I don't understand what's the difference between psi tilde and psi bar.
What is it, the fundamental? No, sorry. No, these are different fields.
Okay.
Psi and psi bar, if you have a field in the fundamental,
Okay.
psi and psi bar, they are from different respect to Lorentz. See, one is alpha and the other is alpha dot. This means spinor, left moving spinor or right moving spinor, or both in the fundamental. Psi tilde is a spinor in the anti-fundamental. It's a different representation. Okay? In other words, one is a vector like this, the other is a vector like that.
But it's still,
Two different fields.
but it's still in the fundamental of the SU2 of Lorentz. Because you've got the same,
Yeah,
you've got the same Lorentz.
They transform, psi and psi tilde transform in the same way with respect to Lorentz, but in a different way with respect to
Of the gauge.
of the gauge.
And this is where you have
They are two different
alpha
fields.
instead of alpha dot in the psi tilde case.
Sorry, say again?
And this is where you have alpha instead of alpha dot in the psi tilde case. Because
No.
it's
Also, it's
Yeah, but
half
yeah,
alpha.
that's right.
Same. It's the same.
Yes, okay.
So it's the same
The alpha is the index of the representation of the SU2 of the Lorentz group.
of the Lorentz. And alpha dot is the Lorentz, because Lorentz, remember, is SU2 times SU2.
Yes, yes.
But if left moving, let's say what I'm saying is that for self-dual connection, only the left moving fermions are not trivial, while the right moving fermions are trivial. Okay? For anti-self-dual will be the opposite way. Okay? And the point is that okay. Now, this is my guess. Okay, I didn't say you speed. What is K? K is a matrix, it's a numbers. These are matrix of numbers. K and N and bar. For the moment, this is an answer. What I will do now is I will plug in the equation of motion and see what condition should satisfy this K in such a way that this satisfies this equation. For the moment, I just use the symmetry. These are the objects that I have, and then I try to build something out of this.
Excuse me. The fact that you can give this independent solution of psi bar is because you're in Euclidean, right? Or not? Because in Euclidean, these two guys, they're not related.
They're independent, exactly. You're saying, in Minkowski, the two, you would say that the one is the complex conjugate. Here, they are two completely dependent. Okay. Okay, now let's check the equations. Let's start from psi, and we start to check all these equations. Okay, let's start from the side. We want to compute the covariant derivative. Sorry, I cancelled the equations. Let me write here the equations. Sorry, yes. Sorry, and I also don't say what is the scale. No? Solution to this Laplacian, the last equation was Laplacian of phi is equal to c. Okay? This is also scalar. Okay? This is trivial solution. All these are solutions. Now the only thing that we should check is that for these three guys satisfies the dialectic. For example, notice that if I start to turn the interactions, remember there was Yukawa interaction, phi, psi, psi. If I start to turn the interactions, this equation for the scalar start to change. No? Because here now it will appear some Fermion interaction. And then when I say zero, this means zero to this object. Then you can start to turn the interactions and start to say, to modify all what I will say. Then all what I will say are the solutions to linear objects. Then you can go ahead. Okay.
Sorry. Isn't this a perturbative procedure in some sense?
It's perturbative, exactly. On the coupling, for example, and then
So
you are turning off
coupling is small.
to very small. Yes. But as we say, you can either say either perturbative on the coupling, or you could say it's perturbative on the fields, or field are very small. Then you can forget about the cubic terms and so on. Or if you have any parameters you can perturb your theory, you can do. What we will see is that for this particular theory, supersymmetric theory, we will stop this detail, small perturbations cannot change some of the quantities. There are some quantities that can protect about small perturbations. The idea is always that boson and fermion contribute opposite. But for all this correction we can say, but okay, it's true. You can think of that as just a perturbative. Okay, then this is the equation. We want to prove that this is C. You see, this was alpha dot alpha. This is what I call the. Sorry, I forgot here a factor half. Correct, you can see. This is exactly what I call twice d bar alpha dot. Okay, therefore, what I will compute is this. I want to prove that this is. Okay, let's compute. D bar, what is that? This is D bar alpha dot alpha plus A alpha AM sigma M alpha. Acting on side. Okay. Now let's see. Let's first, you see, this derivative depending on x is only either here or here. Okay. Let's compute. Let's compute, for example, the covariant derivative of this object. Why I do that? Because I will use this everywhere. Every time I find u, then I will do just once the calculation of d bar of delta and the bar of delta bar, and then I will every time use this result. Then this is an intermediate step. Okay? Then we say this is d bar alpha dot alpha u plus an sigma bar n alpha dot alpha. Okay, now what I do here is, as usual, I want to use this identity. Here. The question is, every time I have a derivative acting on u, this I don't know what is this. But I know what is in delta. Therefore, I take this identity, and I put here somewhere. For example, you can put in this case, for example, from here. I didn't say it. Imagine I put from here this identity. U bar plus delta F delta bar times this. I'm just multiplying these things by that. Now, I know that u bar times u is the identity. Therefore, this derivative I can pass here. Sorry, all this is, yes, it's okay. Now let's see this first term. The first term with that, I can write like minus u sorry. This is just u bar du. What is that? A. It's just A. Okay, but then I did here wrong, because you see, U is a matrix lambda times U. Therefore, lambda times U. Therefore, the A acts from this side. This is not correct. A, okay, this can be here, but A is acting from this side. A, because A have an index U. A. And since it's acting as from this side, you should get also side. This is how you define the covariant derivative. This delta bar is acting from this side You see, you can just read from the index of U. From this side with a minus. So here there is a minus. And if delta is up to A hat. In other words, I mean, you can just read from the index, but fundamentals act from one side and anti-fundamentals act from the other side. Okay? The other way of saying it is that you can see. Okay? Now, this term here, with this term, if U times A, while this with this, U bar times U is 0, it's minus U times A. So these two terms cancel. Okay? This term with this, and this term with this, cancel. Okay? Therefore, I have plus this term, delta F, delta bar, V bar, alpha bar, U. Okay? And then this term is delta bar times U. Which is 0. So that's all. And we say that this derivative is delta F delta bar V bar alpha U. Okay? But again, still, this is not what I want. I have the D acting on U. I don't want the D acting on U. I don't know what is that. I should pass here. You know, delta bar times U is 0. Therefore, this is equal to minus delta F T bar alpha dot alpha. Sorry, all these are alpha is alpha dot alpha. Alpha dot. So, delta bar. Okay, then we find already that T bar alpha dot alpha U is equal to minus delta F D bar alpha dot alpha delta bar. You see, it's always, if you have this written somewhere, all the ADHM algebra is very simple. It's just moving, using this equation to move the derivative always on delta. We know the derivative on delta. We don't know the derivative in U. Every time you have the derivative in U, you bring it to delta. It's just a bit heavy trying to keep track of the indices and so on. But remember again, all this you will do 1 or 2 times in your life. And after you learn and you understand what is going on, you don't need to repeat again. Now you can do the same thing for D of U. U bar. Now. Okay? And what you find is, okay, of course, you find just all these steps you can apply in the same way. The only difference will be that now A will come from this side and with a plus sign here. Okay? And the final answer is exactly just this, the opposite of that. You find D alpha dot alpha of delta F delta bar. It's just you have just the Hermitian conjugate of this computation. If you want to see even easier, okay, I did here debug, this is what I need, but I can also say this. This is also true. No? All what I say here, I never use this index. Then you see, this equation is just the. If this is true, you just do the Hermitian conjugate, this should be true. Okay. Now you multiply by sigma n bar alpha dot alpha, and you get the equation here. Okay? Or if you don't, you can't repeat it. But okay, just the Hermitian form. Okay? Then now I can easily compute this. Okay, the equations I no longer need because you see it's just this is okay. Now let's compute this one. D bar dot alpha psi alpha is equal to. There are two possibilities. Either the derivative act on f, so you find k t alpha dot alpha f p bar alpha u, or the derivative act on psi, or sorry, act on the u. The derivative can act here or act in u. And together with the connection, we can use this formula. This is minus okay, k f p bar alpha, and then when it acts on u, it brings here the delta f p alpha dot alpha delta bar. K f p bar alpha, and then act is d of u. D of u is this minus delta f p alpha dot alpha delta. Okay. Now I should use this. What is d of alpha? D of f. D of f, we can compute from here. Remember, the only thing that I know is d of delta. Okay? Every derivative I should relate to that. Let's compute it from here. Then you see that dn of f to the minus 1 is equal to you know what is that? If f would be a number, you would say that this is dn of f over f squared. But f is a matrix. Okay? The formula is exactly the same, it's just that this f minus 2 you write like f minus 1. F minus 1. For a matrix, this is the rule. Okay? If not, think of f as a number, this is just df.
It is also minus sign.
Sorry, there was minus. It's minus df over f squared. Just f squared, like a matrix, should be. Okay? Now, if I know also that this derivative is also dn delta bar delta plus delta bar dn. Now, notice that this is B. This was okay. For the version I Okay, the question I want to prove is the following. Is D, now I should multiply this by alpha dot alpha F. See, this will be, I multiply by F here and by F there. Okay, therefore 4. This will be minus F B bar alpha dot delta B bar alpha delta alpha dot F, and will be also equal to where I use the fact that B alpha delta alpha dot is equal to delta bar. Essentially, these two terms give the same contribution because there is this commutation. B is roughly the derivative of M. Remember, the derivative of M on sigma bar is just sigma M. Okay? Then, and B was defined here by this relation. B is just the derivative of delta respect to it. And this is just epsilon, it's like the identity matrix. Therefore, these two things commute. Therefore, these two contributions give the same. Therefore, I can simply say that this is equal to twice this. Sorry. There's no twice because they were this alpha dot, beta dot. Okay, because okay, it's better to do this by yourself.
You have a 1/2 in the definition of the
this F is a matrix k by k, not k by 2k. There is a delta. There is in this relation there is a delta alpha dot beta. Okay. Therefore, if you want to compute the area of the flat, you should compute the trace of that. And this will give two terms. Then essentially, what I'm saying that each of them gives the same contribution. This is the minus. The F coming from here and here. And here you should B is just this guy. I just take this equation, multiply by sigma n, 1/2 sigma n dn, and I get these two alternatives. I use this commutation. This is just the fact that B is proportional to the derivative. And I find this funny relation for the derivative. Therefore, every time I find the derivative of F, I will use these two relations. Okay? Please do as an exercise, derive this from the Euclidean side right here. This is the only thing that you need to use is this and this. Okay? Or this as this. Okay? But then you see that this time here, df is exactly this term here cancel exactly this term. So you see here, this derivative of f, k, the bar of f, I now use this relation, was derivative of f was f. Let's use this. F b bar is minus f b bar alpha delta alpha dot f. Okay, this is derivative times b bar alpha minus k is here, f is here, b bar alpha dot is here, therefore k and f is common to both. And here I have b bar alpha with the index down, delta, f, and this b bar of f is again b bar alpha dot in delta is b bar. B bar alpha now I want to put it this way. You know that this is contraction here. Every time you have B alpha is the same as minus the alpha. Yeah. Here indices are raising and lowering with the epsilon term. This is just epsilon alpha beta b. In SU2, there is the epsilon tensor is element. You raise and lower indices with this epsilon tensor. Therefore, I can simply move this down and move this out and put a minus sign. Okay? And then do the same with delta. Here there was d bar, it was d bar delta f, and here there was, let's write this, this was delta alpha d bar. I mean, this computation is very bad to do in the Blackboard. In any case, you now follow the image. You already see that the field have the same structure. Okay, now you should check the signs and see that this is just. Sorry, I'm not able to do this now in the plan. Try to do it. If you are not, if you have problems, we can try to do it together in the next. It's just very simple. It's just you should keep into track these things. Every time you raise and lower index, you should do with the epsilon. So the structure is the same, and then you get that this is 10 minutes. Okay. Then for psi tilde is exactly the same. No? This is just the complex conjugate derivation for that. Sorry, the Hermitian conjugate of the computation we did. No? Then let's do this one. Enjoy. Again, I should use just these relations. Therefore, I should do d of u bar okay? It should do this derivative. Now, the derivative can have either here. Now I will not write indices in such a way that I don't make this confusion here. Just to see, apply this formula. D of u bar, if, okay, everything will contain u bar here, and so u at the end. Okay, now we should compute what is inside. D acting on u bar give me minus u bar d of delta, this the t delta, f delta bar multiplied by everything, m f b bar minus b f m bar. Okay, this is if I act on this u bar. Now, if I act on this u, I get all this. Multiplied by this delta f d bar. So u is already, and again we sign minus. Sorry, there was some question. And then the last is when I act in f, plus m df b bar minus b df m bar. Okay, this is the formula. Okay? Now let's collect the various terms. For example, the terms that contain m in the beginning. Okay? Here I have this term here, df p bar. Okay? And I have this term here. Okay, this one, you already write. Let me write also this one. Okay? This is minus f p bar delta f b delta bar. Okay, then I write these two terms. Okay. Then I have also the terms that contain m bar, the conjugate of this guy, for example, m bar, this guy, for example, is minus b ef, and okay, this is this guy. Sorry, this is this guy. Minus BDF with m bars. And what else? Let's start with this one. M bar is also here. Okay. Then this is, sorry, there is no M bar here. The M bar was already the same. This M bar contains here plus D delta F delta bar B F. Okay. Then this was this term. Okay. Clearly, I'm collecting the terms and I know if I have something in mind, of course. This is that. Then what is remaining is this minus d delta f delta bar n f b bar. This term, and what else? This guy. Plus M P. Sorry, which was the term I'm missing? The term that we're missing was here. Was plus B F M bar delta F B. Okay, now you already see these terms. Again, you see df is f b delta f, and b bar is d b bar. Of course, you should check just the signs. These two terms cancel. The terms is again df is, you see, b is d delta, and df is f delta bar bf. These two terms cancel. Okay? And then the last two terms, and what we found is that u bar times this term, let me write it this way, b, this is b, f, delta bar n plus m bar delta here f b bar. Again, I will not follow the signs, but you already see that here there will be a b, and here will be a b bar, but this b will be b bar alpha, and this will be b alpha, b bar alpha. You should flip the two, one of the two, and you get the relative sign plus. Okay? And the crucial point is that all this cancel except for this. So the only way that this is 0 is this. So you see, for fermions, you find a sort of ADHM constraint, but for fermions. This is a fermionic ADHM constraint. Therefore, the adjoint fermions should satisfy a given intelligent matrix M that satisfies a fermionic ADHM constraint. This you would expect in the next lecture when we will do supersymmetry, because supersymmetry relates boson and fermions. No? Then if bosons, if you have an adjoint, if you have supersymmetry, this means that the vector should be related to a fermion in the adjoint, in the same representation. Then we will see that this constraint is the supersymmetric analog of this. Okay? In a supersymmetric system. But in general, if you have an adjoint fermion, this will satisfy this. Then this is a sort of fermionic analog of the ADHM. Okay?
Excuse me? The matrix M appearing in the adjoint fermions is just a matrix of number.
It's a matrix of numbers. N, K, N and K are just matrices of numbers, unlike the delta. Sorry, not the delta. The delta, you remember, has a part with just a matrix of numbers.
Yep.
Let's write now this construction. I don't know what time is. Okay, then we do the next okay, here we finish, because this finish for the fermions. You see, we already solved all the equations for the adjoint and for the fundamentals. The details are really not important. You will see that if you talk to most of the people that work in Instantons series, they have never did it. They have never done this computation. It's something that you learn, you read in there, and you will never use again. The same that we will see that for the particular class of series that we are studying, all the details are not important. Okay, the important is that there exists a solution that is given by these matrices, that this matrix has some dimensions. I mean, the important are the numbers, not the precise details of the. But I think it's very useful for you to get familiar with this, because if you will work, you will need at some point some of them, okay? Not all of them, some of them. If you just repeat some of, just to get familiar with this Lorentz indices, the matrices, and so on. Okay, then the next. Okay, that was. I will ask to Gianluca. No, sorry, I already asked to Domenico. For the lectures of Wednesday.
Wednesday, yes.
Tomorrow. Okay, the problem is that I have a flight on Friday at 5, and it's not obvious if I finish after 1:30, I can get the flight. And the other speaker also is leaving the same day. Therefore, it's possible, it's too heavy for you to have 2 lectures of Instantons tomorrow. It's okay. We can take the lectures of Friday, we will move to tomorrow. Okay?
Cosa, da 11:30 sostituisce Susi.
Ah, è Susi per venerdì. Ah, quindi un cambio tra le due. Ok. E quindi facciamo praticamente una mattina solo. No.
No, sono 6 ore di Instantons domani.
No, 4.
4 ore di Instantons.
No, 6 no.
6 ucciderebbe tutto.
No. Poi nessuno vuole